In this video, I'm going to show you the best way to get started with FreeCAD. We're going to model this technical bike stem from scratch. I'm not talking about that old basic design you might have seen before. That was the old way. This new version is much cleaner, more professional, and way easier to build thanks to the new 1.1 tools. But more importantly, I'll show you how to avoid common mistakes and especially how to fix them when they happen. Let's jump into it. For this video, I'm going to assume you're starting completely from scratch, and I'll do my best to explain everything step by step. However, if you ever feel lost, you can download the 3D file and all the sketches from my Ko-fi page. It's completely free, but if you'd like to support the channel, you can leave a donation. Thanks in advance. To start a new project, FreeCAD offers several options. Beyond being a fantastic modeling tool, it also allows you to handle assemblies, 2D drawings, and BIM for architecture. You can even generate CNC toolpaths for machining and perform mechanical analysis on your parts. But what interests us here is the foundation of all processes, which is modeling. For this, we are going to click on the parametric body icon to start directly in the right workbench. Since this is a tutorial to teach you how to use FreeCAD, I am not going to overwhelm you with too much information. We're going to do everything within the part design workbench. It's the most intuitive tool for creating 3D shapes. When you're just starting out, stay in this workbench. It has everything you need. In the tree view on the left, you can see that a body has already been created. If you are coming from Fusion or SolidWorks, pay attention. In FreeCAD, the body is a container that comes first. It holds its own planes and axes, and everything we build stays inside it. The simplest approach to modeling this stem is to visualize the manufacturing method. An object like this is generally machined via CNC. Since the machine starts with a raw block of aluminum, we'll mirror that process by identifying our base shape. Our first step is to create a simple solid block, which we will then refine to reveal the final part. From this view, we can see that the object is symmetrical. This is something you must take into account when modeling, as it can save you a significant amount of time. Always try to determine if your part has symmetries before you start creating it. So, if you've been following along, we're going to create the primitive shape, which will look like this. I've set the final shape of the stem to transparent, so you can see that this is indeed our starting primitive. To start the modeling process, we are going to create a sketch. A sketch is a 2D element that allows us to create a 3D shape. Make sure you are inside the body. It should be highlighted in the tree view. Then click on the sketch icon in the toolbar. Since this is our first sketch and we haven't created any faces yet, we need to choose a base plane. The planes are named after the axes that form them. Here we want to create a sketch that will be the side view of the stem, so the most logical choice is the XZ plane. When you select a plane, the 3D view automatically aligns itself to be perpendicular, making it feel just like you're drawing on a sheet of paper. To control the view and move around, it's important to know the shortcuts. If you chose the Revit style, zooming in and out is done with the mouse wheel. Pane, which is flat movement, is done by clicking and holding the mouse wheel, and rotating the view is done by holding Shift while clicking the mouse wheel. To realign the view so it's perfectly perpendicular, you can click on the front face of the navigation cube or use the Align View to sketch icon. If you want to change your navigation style or explore the different options, you can go to the Edit menu, then Preferences. Under Display and Navigation, you will find Mouse Selection to see all the different controls. What makes the Sketcher so powerful compared to a simple drawing is the ability to link your lines together by applying constraints. In the toolbar, the icons with white lines and red points represent the drawing tools, while the ones in red are the constraint tools. The strategy is simple. We're going to create geometries and then constrain them. For example, we'll create a rectangle. Click on the rectangle tool in the toolbar. Near your cursor, you should see the shape you are about to create appear. At the bottom of your screen, you will find instructions for building our shape. For a rectangle, you need to make a first click to place the first corner. As you move your cursor, you should see boxes appear for entering the dimensions of your rectangle. Simply type a value, for example 100. This will lock the width, and you will then only be able to modify the height. By pressing Tab, you can switch to the vertical dimension and give it a value of 100 as well. To confirm the creation, just left-click. Near the lines of your rectangle, you should see red symbols appearing. These red symbols represent the constraints that were automatically applied by the software. Since we asked to create a rectangle, it automatically added vertical and horizontal constraints, which maintain the perfect shape of the rectangle. Near your cursor, you should still see the rectangle symbol, which allows you to continue creating more rectangles. If you want to stop using the rectangle tool, simply press Escape or right-click. By left-clicking and dragging a corner of your rectangle, you'll notice that you can move it around freely, which isn't necessarily a good thing. You absolutely must lock your drawings so they don't move, as this can lead to reconstruction errors, and believe me, that's the last thing you want. In our sketch, the only three fixed things are the origin point and the green and red axis. The simplest way to constrain this is to take one corner and lock it onto the origin. To do this, we're going to select the coincident constraint tool, then select the origin point and one corner of our square. This will automatically move our geometry and it will turn green. This means it is fully constrained, and that is exactly what we want. Just like with the rectangle tool, to stop using the coincidence constraint, you must right-click or press Escape. Now let's get down to business. Our goal here is to recreate this sketch. It's another rectangle, but this time it's positioned differently. This sketch will be used to create the base shape of our stem. What's interesting to understand is why it's positioned this way relative to the axis. I'll show you the final stem in transparency so you can see. The answer is simple. I want the green axis to correspond to the location of the stem hole that joins with the fork. Later, I want to be able to easily modify the length of the stem, the value of 66, which will make it much easier to create a variable. Plus, the red axis corresponds to the center of the stem. When I place the handlebar hole, I'll be sure to always be right in the middle. We're going to start by deleting the previous square. We'll perform a box selection by holding down the left click and dragging. Our square will turn blue, and then we'll press the delete key to remove it. Then we're going to grab the rectangle tool again. We'll start the drawing in the upper left corner and extend the second point to the lower right corner. We're going to draw it freestyle without entering any specific values for now. As explained before, we're going to constrain the rectangle on either side of the green axis to make it easy to access later when creating a variable. To set a value relative to the green axis, we'll use what is arguably the most important constraint tool, the dimension tool. This will allow us to define a specific distance between the far right point and the green axis. Select the tool, and by clicking on the far right point, it will automatically generate a horizontal distance between the green axis and that point. Make another left click to place the dimension, and a window will open where you can enter a value. Here we're going to enter 66 millimeters. Then you can click OK or simply press Enter to confirm the dimension. One of the new features in FreeCAD is the automatic scaling of the sketch after the first dimension. Since we drew our rectangle randomly, applying that 66 value automatically resized all the other lines to maintain the scale relative to that number. It's pretty amazing, and honestly, it's something Fusion users don't even have. Now we're going to set a dimension for the left point. This time, instead of just selecting the point, we'll select the origin point and then the left point. Move your mouse upwards to get the horizontal dimension, otherwise you might end up with a relative or aligned dimension. It's a different workflow, but it's a very interesting one to know. Then we can give this segment a value of 32 millimeters. Now we need to set a vertical value for the left segment, so we'll select the 2 points and give them a dimension of 50 millimeters. An even simpler method, if you prefer, is to click directly on the segment itself. This will automatically create the dimension without you having to select the individual points. Now, if you grab the top corner and try to move the geometry, you'll see that it's well constrained horizontally, but not vertically. If you remember what I said earlier, we want the red axis to be at the center of the stem, meaning it needs to be an axis of symmetry. To do this, we're going to use the Symmetry Constraint tool. To make 2 points symmetrical relative to an axis, you can select the first point, then the axis, and finally the second point. Or you can just as easily select both points first and then the axis. In this case, the tool is quite forgiving. And here's where the drama begins. Your sketch turns orange, which means there's a problem. But don't worry, this is typical behavior because a crucial option isn't checked by default. By applying a symmetry constraint, it conflicts with the vertical constraint that was automatically created when we drew the rectangle. FreeCAD considers this redundant, because the symmetry between those 2 points already implies a vertical alignment. FreeCAD can handle this automatically. To prevent this issue from happening again, go to the Constraints menu, click the small arrow next to the wrench icon and check the box Auto Remove Redundant Constraints. Unfortunately, it won't fix the current one retroactively, but it will for everything you draw from now on. To fix it here, click on the number in parentheses next to Redundant Constraints in the task panel. This will highlight the problematic constraint. Then just hit Delete to unlock the sketch. Don't worry, now that the box is checked, you won't see this problem again. Our sketch is now fully green and defined according to our goals, making it easy to parameterize later on. We can click Close to exit the sketch. We can now create our first solid. To do this, we will perform an extrusion, which consists of adding volume to our sketch along its perpendicular plane. In FreeCAD's part design workbench, this operation is called a pad. To do this, first make sure the sketch is properly selected and highlighted, then click on the pad tool. This tool can be accessed either via the task panel on the right or through the toolbar. A new menu appears in the task panel. This is where we can choose the extrusion distance. In this simple case, we just want to set a height. But remember, we're only modeling half of our stem, so we need to enter an extrusion value that represents half of the total thickness. In this case, it will be 22 millimeters. You should see the green preview update in the viewport. Once that's done, you can click OK to create the solid. Congratulations, you've just obtained your very first 3D object, and this is only the beginning. Before heading to the next step, I'd like to take a moment to introduce the sponsor of today's video, PCBWay. They are simply leaders in PCB manufacturing, 3D printing, and CNC machining. You just upload your file, select the options, which are very detailed and complete, and you get an instant quote. I've tested their service several times, and the results were always perfect. Right now, you can see this bike chainring they machined for me. The quality is flawless, the tolerances are spot on, and all of this for a very low price, even for small quantities. Don't hesitate to take advantage of their offer, especially since you get a $5 coupon on your first order. They truly are the perfect partner for your prototyping needs, or even for mass production. A huge thank you to PCBWay for sponsoring this video. Now we're going to focus on removing material to allow the handlebar to pass through the front part of the stem. I've put the solid we're aiming for on the screen, with the full stem in transparency, so you can see exactly where we are in the modeling process. To do this, we're going to use the same technique. We'll start by creating a sketch, so click on the New Sketch tool in the toolbar. Just like before, we want the hole to be made on the front plane, so we are choosing the XZ plane. I think you can see the problem coming. We're sketching on a plane that's behind the solid. We can see that the axes are hidden by the part, and if we pick the circle tool and draw it where we want, it's invisible, it's hidden behind the object. Fortunately, we have a tool that allows us to create a section view of our part, so we can see our drawings. To do this, click the Toggle Section View tool in the menu. Now you should see the red and green axes appearing through the part. You can then go ahead and grab the circle tool and create it on the red axis. Before clicking, make sure you see the coincidence icon to ensure that the circle is indeed properly placed on the axis. Left-click once, then enter a diameter of 22 mm and press Enter to confirm. To stop using the circle tool, simply right-click or press the Escape key. Normally, your circle should now be constrained only to the red axis. The last step is to give it a horizontal dimension between the origin and its center. Use the Dimension tool and click on the center of the circle. This will automatically give you the distance from the origin. Enter a value of 40, then press OK or Enter to confirm. Our circle is now perfectly placed, and the lines have turned green, so we can exit the sketch by clicking Close. To remove the material, we're going to use a pocket operation. Just like with the previous step, make sure you have Sketch 1 selected, then click on the Pocket tool. You will likely see an error appear. Don't worry, that's normal. In this case, FreeCAD is trying to remove material into empty space, which triggers the error. That's why in the task menu, you need to check the reversed box so that the material removal happens on the correct side. To ensure the material is removed all the way through, we could enter a dimension greater than the thickness, so more than 22 millimeters, but that's not the correct way to do it. If you ever change the initial thickness, the cut might no longer go all the way through. That's why under the type setting, you should change it to Through All. This ensures that no matter what happens, the hole will always be there. You could also choose Up to Face and select the outer face, which works too, but keep in mind that reconstruction errors can happen if FreeCAD forgets which face was selected. So, the safe call here is to stick with Through All and click OK to confirm. We're now going to start giving the part some character and a sleeker shape by performing another material removal. Here is what we should obtain after this step. To achieve this, we're going to start with a sketch. So click on the New Sketch tool and choose the XZ plane once again. The part is hiding the sketch just like before, so click on the Section View tool to see through the material. The keyboard shortcut is Q followed by S if you want to save yourself some time. Our goal here is to recreate this sketch, and the trick is to use the existing geometry as a reference. However, if you pick the Line tool, for example, and try to snap it to the edges of the model, it won't work, and your lines won't be coincident. If you're coming from Fusion, it handles this automatically, whereas in FreeCAD, you have to manually project the edges. To do this, we're going to use the External Geometry tool. With this tool, you can cherry-pick only the edges you need, or you can project all the edges of a face at once. That's what we're going to do here. Just left-click on the face. You should see the projected edges appearing as solid purple lines. Be careful though, because these are drawing lines, not construction lines, meaning they will be included in future operations. Now, when we grab the line tool and try to draw, you'll see that the line snaps perfectly to the edges. Now we can recreate our sketch. To do this, we'll use the polyline tool, which allows you to create continuous lines. We'll start drawing by snapping to the right edge and moving horizontally. You should see the horizontal constraint symbol near your cursor. Create a first point past the green axis, then continue the path up to the top edge. Next, we'll stop our line by pressing Escape or by right-clicking. Then we'll resume the drawing a bit further along by placing a point on the top edge and another one on the far right edge. Right-click or press Escape to stop using the tool, then resume the path by starting on the left edge and going down to the bottom edge. If you're wondering why I stopped the drawing each time, it's to avoid having multiple overlapping lines. This helps prevent certain errors that could cause your operations to fail later on. Stop the path, then resume it a bit further along. Create a second point in the middle of the face, then move horizontally all the way to the far left edge, making sure you see the constraint symbol. Then stop the path. Right now our sketch is drawn, but it's not yet constrained. To fix that, we're going to use several constraints. The first thing we'll do is make these two lines parallel. To do this, we'll use the Parallel Constraint tool and then click on both lines. We're going to do the same thing for the other two lines. Still using the same tool, simply click on the first edge and then the second one. Our goal here is to recreate a rectangular shape. Since we already have our lines parallel in pairs, we just need to use the Perpendicular Constraint tool and select these two edges to obtain our rectangle. Now all that's left is to add dimensions to fully constrain our sketch. We'll start by setting a horizontal value for the first point to the right of the green axis. It's the same logic as before. I'm setting distances relative to the green axis so that it's easier to use a variable later on. So for this one, we'll enter a value of 23 millimeters. For the point below, we're going to give it a horizontal value of 28 millimeters relative to the vertical axis. Next, for the small line at the top, we're going to give it a horizontal value of 10 millimeters. We'll also set a 10 millimeter gap between the 2 points on the top edge. Now at the bottom, for the 2 points on the bottom edge, we're also going to set a horizontal gap of 10 millimeters. Now we need to take care of the 2 points on the far left. You can see they still influence the sketch quite a bit and aren't constrained yet. I want these 2 points to be symmetric relative to the red axis. You already know how to do this, as we did it just a moment ago. To do this, we'll use the Symmetric Constraint tool, then select the top point, the red axis, and finally the bottom point. Even now you can see the sketch isn't fully constrained yet. We still need to set the distance between these 2 points. So we'll use the Dimension tool again and enter a vertical value of 32 millimeters between them. So now my sketch is complete and you can see that it contains several closed loops, which I'm pointing out here with these arrows. Keep this in mind as it's going to be very important for what comes next. With Sketch 2 properly selected, we're going to launch a pocket operation. And here we go, disaster strikes once again. We've hit the dreaded "wire is not closed" error message. To be honest, I made this mistake on purpose to show you that FreeCAD can't handle sketches with multiple contours, at least not unless you change one tiny setting that can be a real lifesaver. I'll show you. Press Cancel to close the operation, then we'll go into the tree view and hide the pocket operation so we can see our sketch clearly. Since version 1.1, we can now generate faces within our sketches from closed profiles. The tool is still fairly new, which is probably why it isn't enabled by default. To activate it, select the sketch, then go to the Data Properties tab on the left. Look for the Make Internal line and check the box to set it to Yes. You can see that some of the internal contours of the sketch have turned blue. This has generated faces that we can now use for our pocket. As I mentioned, this is a new tool, so it might not always generate every single face. In this case, it didn't create the one in the middle, but the tool will continue to improve over time. The faces we're interested in are the ones on the periphery. We're going to select them one by one while holding down the Control key. They should turn a slightly purple color once selected. Then we'll click on the Pocket tool to launch the operation. Don't panic, we've got another error message, but this one isn't about our profiles. It's just that the pocket is trying to cut in the wrong direction where there's no material. So we're going to check the reversed box to make sure the pocket goes the right way. Then under Type, we'll set it to Through All to ensure it cuts all the way through. And finally, we'll click OK to confirm the operation. Here I've shown you the easiest method to understand by combining several operations and sketches. However, I want to point out that we could have made the same part using only one sketch and a single pad operation, but that would have required creating a much more complex sketch, which can be overwhelming, especially for your very first sketch when you're starting from zero. The trick here would have been to start with the rectangle sketch and convert it into construction lines. Then you'd place the solid outlines inside so that the pad operation has both an outer and an inner profile. Internal contours are treated as exclusions, which is what creates the opening automatically. That was just a little pro tip for your future models. Back to our model. We're going to keep improving the look of the part by creating some chamfers. A chamfer is simply breaking a sharp edge by creating a small flat angled surface to make the part less sharp and more aesthetically pleasing. I'll show you two different methods for this. For the first one, we'll select the back edge of the stem and then click on the Chamfer tool to create it. Generally, a chamfer is a 45-degree cut, meaning it's constant on both faces, as you can see here. But we're going to create a chamfer with different distances in each direction, allowing us to achieve an angle other than 45 degrees. To do this, in the task menu under the type parameter, we're going to change equal distance to 2 distances. In the viewport, you'll notice that we can tweak the preview using the small arrows. As shown here, having 2 distances allows us to create a much more interesting shape. For the size, we'll set the first direction to 10 mm and the second to 38 mm. Then we can confirm the operation by clicking OK. The second method, which is less elegant and perhaps a bit more time-consuming, is to use a pocket operation. The chamfer we want to make is the one at the top back of the stem, as shown on the screen. I'm showing you this method because it can be a lifesaver if the standard chamfer tool fails to work on more complex shapes. To do this, we'll first create a sketch by clicking the new sketch icon, and once again we'll choose the XZ plane. Just like with the previous operations, we're going to use the section view tool so we can see through the part and draw our sketch. The path will be based on the stem's contours, so we'll use the external geometry tool to project the adjacent edges into our sketch. To avoid the famous wire is not close message, we're going to select the 2 projected lines and convert them into construction lines. These lines are paths that help us build our sketch, but are hidden during operations. They are there to guide us, but they don't interact with the final 3D shape. Next, we're going to use the polyline tool to create a closed triangle in the corner between the 2 construction lines. Make sure to watch for the different coincidence symbols near your cursor to ensure you're snapping correctly onto the projected lines. Next, using the dimension tool, we're going to set a distance of 12 mm for the horizontal line and 3 mm for the vertical line. Our sketch is now fully constrained, so we can go ahead and exit it. We're going to remove the material using a pocket operation. To do that, click on the pocket tool, then in the task menu, just like with our previous operations, you'll need to check reversed. Set the type to through all and then confirm the creation by clicking OK. There you have it, 2 ways to create a chamfer. The direct method is more elegant, but if you ever find yourself stuck with the first option, remember that you can always do it manually using the second method. Another ultra important tip for any 3D project is to rename the different operations in the tree view. As you can see on the left, it's starting to fill up, and if you ever want to modify a feature later on, it can become a real nightmare to find the right one. So, using the F2 key, we're going to rename the body to stem, the pad to pad primary shape, the pocket to pocket handlebar, and the second pocket to pocket main shape. We'll name the first chamfer big back. Be careful not to mistype a couple of letters there, or it could get weird. As for the last pocket, let's call it chamfer small back. Again, watch your spelling, or it might end up sounding like an insult. We're also going to hit our best Ctrl S. Even though FreeCAD is pretty straightforward and the crash recovery works well, it's always a good habit to save frequently. So give your file a very original and exotic name, something like stem, and then hit save. Now we're going to split our stem to detach the front part from the main body. This is what will allow us to remove the faceplate so we can slide the handlebars into the stem. For this split, we're going to leave a gap of several millimeters to ensure the bolts can be tightened properly. We're going to use the same pocket technique as before. To do that, let's start by creating a new sketch, and once again we'll choose the XZ plane. We'll also enable the section view so we can see through the model. The goal here is to recreate this sketch. And as you can see, we're going to use the external projection tool once again to obtain the edges of the model. With the tool, we're going to select the 2 edges around the break, as well as the parallel edge underneath. To avoid any issues, we're then going to select these projected lines and convert them into construction lines. Now the goal is to create a segment starting from the upper breakpoint and joining the bottom edge. To do this, we'll use the line tool and place our first point exactly on the break. Make sure you see the coincidence icon before clicking, then place the second point on the bottom projected line. Now we're going to make this line perpendicular to the bottom projected line. We can select both lines and then apply the perpendicular constraint. This segment will serve as our symmetry axis for the split. Now we need to draw two more segments. Using the line tool, we'll create a segment to the right of the axis by snapping it to the top edge. Be careful not to snap to the midpoint of the bottom edge. There's a magnetic pull toward the center of the segment, so move far enough away to ensure you don't snap there and create an unwanted constraint. Next, draw a second segment on the other side of the axis, starting from the top horizontal edge and joining the bottom edge. Now, we're going to make these three segments parallel to each other. To do that, click on the Parallel Constraint tool, then select the top segment and the middle one. After that, select the middle segment again, followed by the bottom one. And you should now have all three lines perfectly parallel to each other. Now, we're going to set the dimension for our gap. Using the Dimension tool, we'll click first on the top segment and then on the bottom one. This will allow us to set a 2 mm distance between the two lines. The 2 mm gap might have pushed your line to the other side of the axis. By holding down the left click, you can simply drag it back to the top where it belongs. Now, to properly lock the two segments, we're going to apply a symmetry constraint. Activate the Symmetry Constraint tool, then select the top point first, followed by the green axis, and finally the bottom point. Your two segments should now be perfectly symmetrical relative to the green axis. Now we need to convert the middle segment into a construction line so it doesn't interfere with the feature. Once that's done, we can exit the sketch. I intentionally made a mistake here to show you something that often frustrates Fusion users migrating to FreeCAD. In my tree view, if I hide the last operation, the sketch appears. You can see it's just two separate segments, not a closed contour. If you try to run a pocket now, the operation will fail, and you'll get that dreaded wire is not closed error message. In FreeCAD, you must have at least one closed loop to launch a feature. So let's go back and edit our sketch. To do that, double-click on it in the tree view, and using the Polyline tool, we're going to close the contour at the top and the bottom. This will give us a properly closed contour, allowing us to run the pocket operation without any errors. Once that's done and everything is properly closed, we can exit the sketch and launch a pocket operation to split the part in two. As with the other pockets, check the reversed box, then in the type drop-down, choose Through All. After that, you can accept the creation. Technically, we just created two separate solids within a single body. If you get an error at this point, it's likely because an option isn't enabled. Go to the tree view, click on the stem body, and in the data properties, make sure the Allow Compound box is set to Yes. If it's not, that's why you're seeing an error. This box should normally be checked by default, but it's always good to double check if your operation isn't working. We're going to rework the front solid of the stem. Currently, if we were to mirror it, we'd end up with one single large body. On the final version, you can see that this part is actually composed into two identical solids. To achieve this, we're going to perform a small push surface operation. We want this front part to have a thickness of 16 mm. If you can't remember the original thickness, you can simply select an edge across the width, and the distance will appear in the bottom right corner. Here we can see it's 22 mm, which means we need to subtract 6 mm. To do this, rotate the part, select the face you want to reduce, and click on the Pocket tool. I mentioned the push face, but it's actually more of a material removal than a surface move. FreeCAD essentially treats the selected face as the profile for the pocket. Regardless of the terminology, all you need to do here is set the length to 6 mm and click OK to accept the operation. After that, if we rotate the part slightly, we can clearly see that the front section is no longer flush with the main central face. This means that when we perform the mirror operation, we'll end up with three distinct solids. Now let's work on the central opening of the stem. In addition to reducing its weight, it's what gives the design its character. At first glance, this might seem difficult to achieve, but you'll see it's actually very simple. We want the opening to start 5 mm below the top surface of the stem and end 5 mm above the bottom surface. To do this, we're going to start by drawing the cutout sketch on the top face, and then we'll offset it by 5 mm so it starts exactly where we want. First, select the top face, then click on the New Sketch tool. In this case, clicking directly on the face launches the sketch creation on that specific surface. We don't need to go through the plane selection menu because FreeCAD assumes we've already made our choice. Our goal here is to recreate this sketch. You can see it includes an arc. a tool we haven't used until now. So let's start with this arc. To do that, select the Arc tool from the menu. Your first click will define the center of the arc. Here we'll place the center on the origin, making sure the coincidence constraint appears, so we're certain it snaps perfectly to the middle. The second point will define the start of the arc. To keep things simple, we won't enter a specific value yet, just click to the left of the green axis. To complete the path, we need a third point, so again, to keep it simple, we'll place that point to the right of the green axis. To stop using the tool, right-click or press Escape. The rest of the path will rely on the edges of the part, so you should know how to do that by now. Select the External Geometry tool, then select the two bottom edges of the solid. It's absolutely vital that these lines are set as construction geometry because, as we've seen, they can otherwise cause errors. To do this, select both lines, then click on the Construction Mode tool. Now we need to close the contour. To do that, we'll use the Polyline tool. We'll start from the right side of the arc. When you place the first point, you'll notice the line wants to stay tangent to the center, but we want it to reach the bottom edge. To change this behavior, press the M key. This switches the mode to perpendicular, which still isn't what we want. We want it to be free as a bird, so press M one more time, and now we can easily join the projected edge. Now we need to finish the contour by following the projected edges, but I'm going to make a mistake on purpose to show you how to fix it. Here I'm drawing my line all the way to the end of the projected edge, but that's not what it's supposed to be. We're going to keep going anyway and use the Dimension tool to start constraining our sketch. We'll start by giving our arc a radius of 16 mm. Next, we'll set a horizontal value of 20 mm for the bottom right point. Then we'll try to set a horizontal value for the left point, but as you can see, the sketch turns orange, which means there's an issue. This happened because during the drawing phase, I snapped to the end point of the projected edge. This means it's already constrained. The problem here is that my path was supposed to end before that point. To fix this, I need to delete my coincidence constraint. In the Constraints menu on the right, I can click through the list to find the one causing the issue. By clicking on Constraint 8, I can see the problematic point highlighted in blue. This is the constraint I need to remove. With Constraint 8 selected, I just press the Delete key. And now, when I drag my point, you can clearly see that it's no longer coincident with the end point of the projection. To fix my path, I'm first going to convert this green line into construction geometry. Then I'll select the point and the construction line and use the Coincidence Constraint tool so that the point snaps directly onto the line. I can now go back to the Dimension tool and finish constraining the sketch. I'll start by setting a horizontal value for the point we just corrected and give 15 mm. Next, for the right end point of the arc, I'll also give it a vertical value of 15 mm. A little tip. To see which points are still unconstrained, try moving your sketch around. Here the solver tells me there's 1 degree of freedom left. By trying to drag the points, you can easily identify the one that isn't locked down. In this case, it's the left point of the arc, so we're going to give it a vertical dimension of 9 mm relative to the red axis. The only thing left to do now is to close the contour by joining the 2 points on the construction line. To do this, we'll use the Line tool, clicking first on the left point and then on the right point. This will completely close our sketch. Great, the sketch is now finished, but it's not in the right place yet. Remember, we want the opening to start 5 mm below the surface. To do this, make sure the sketch is selected, then go to the Data Properties tab. Under Attachment Offset and then Position, set the Z value to -5 mm. You should see your sketch move accordingly in the viewport. Now let's create our pocket. With the sketch selected, click on the tool. Our goal is to maintain a 5 mm gap from the bottom face, so we won't enter a fixed value. Instead, set the type to Up to Face and select the bottom surface. Right now, the material is being removed all the way to that face, which isn't what we want. To have the cut stop 5 mm above it, set the offset to face to -5 mm. Now, in the preview, you can see that the operation is perfect. With these settings, the model becomes bulletproof. Even if we change the height of the stem, our pocket will always start 5 mm below the top face and end 5 mm above the bottom face. We can now click OK to confirm the operation. Believe it or not, we've actually finished the bulk of the modeling work. For the next step, we're going to make this stem look less rigid, giving it a more rounded and refined look. To do that, we'll be using quite a few fillets, as you can see in this quick preview. But before we do that, to keep our file well organized, we're going to rename the 3 pockets to Split Body, Push Face, and Cutout. This really helps you find your way around later if you want to change a value. We'll start with the fillets on the top face. We have a lot of them to select. Instead of holding down Ctrl to select them all before using the tool, we're going to do it the other way around. We'll launch the Fillet tool first and then select the edges one by one. This prevents you from losing your entire selection if you accidentally miss a line. This is definitely my preferred method whenever I have more than 3 edges to select. The hardest part here will be making sure to select all of them without missing any, especially those on the small solid at the front. If I've counted correctly, you should have 15 edges selected. It's a bit of a game of patience, but it's very important not to miss a single one. Once you've selected everybody, go to the task menu and change the radius value to 2 mm instead of 1 mm. It's going to look much better. Now we're going to add a larger fillet to the bottom edge of the stem. Since there's only one selection this time, we can select the edge first and then launch the Fillet tool. In the task menu, we'll set the radius value to 10 mm and then confirm the operation. That was just the warm-up. We still have 6 more fillet operations to go. Now let's handle the ones at the back. We're going to select the 2 rear edges and then launch the Fillet tool. We'll give them a value of 5 mm and then confirm. Now it's time for these 2 center edges to get the same special treatment. Select them and give them a 50 mm fillet to get a beautiful, smooth curve. Now let's focus on the cutout. Select the 2 internal vertical edges and apply a fillet with a radius of 1.5 mm. We're going to do the same for the horizontal edges. But here, as you can see, the fillet needs to be applied to several connected edges. You only need to select one single edge, not the whole chain. FreeCAD can automatically detect the entire path, so just select one edge at the top and one at the bottom and give them a 1 mm fillet. Just one last fillet to create, I promise, and you won't hear me mention fillets for the rest of this tutorial. We're going to select one edge of the contour and give it a 0.5 mm fillet to smooth everything out. I don't know if you agree, but this tool really has a magical touch. It can turn a plain, straight, boring shape into something truly interesting and professional, and that's just in a few clicks. Anyway, we're going to rename all these operations in the tree view to stay organized. I'm just going to add their location to the name, like top, bottom, back, middle, cutout vertical, cutout horizontal, and cutout contour. But of course, you can leave them as they are if you're feeling lazy. Right now, the front part is just floating in mid-air like a helium balloon. We need to create some holes so we can insert some bolts. To do that, we're going to create a sketch for their placement. Rotate the part, select the front face, and click on the sketch tool. We want our holes to be perfectly centered on the part. To achieve this, we're first going to use the external projection tool and then select the top and bottom edges. Next, we need to convert these projected lines into construction lines to avoid any issues later on. To find the center of the face, which will allow us to set our dimensions, we could use several techniques. Personally, I like to draw a line that starts from the midpoint of one edge and joins the midpoint of the other. Then I'll just convert this line into a construction line as well. Next, using the point tool, I'm going to create 2 points that will mark the locations for my drill holes. The goal here is to snap them correctly onto the construction line so they stay perfectly centered. I'm then going to create a 3rd point in the middle of the line, keeping a close eye out for the symmetry constraint symbol before clicking. This guarantees that the point will be perfectly centered on the line. Next, using the dimension tool, I'm going to set a distance between the center point and the top point of 16 mm and a distance of 15 mm for the bottom point. Keep in mind that my hole tool will use these points to create the drillings, and I want to have 2 holes on my solid. My sketch is now fully constrained, so we can go ahead and exit. In the task menu on the right, click on Hole. As you can see, it's creating 3 holes instead of the 2 I wanted. I actually forgot to convert the center point I used for positioning into a construction point, so FreeCAD is placing a hole there too. No worries though, let's jump back into our sketch. Select the center point and convert it into construction geometry. And now when we launch the hole tool again, we only have the 2 holes we're actually interested in. Right now it's just a simple straight hole, but we want the bolt heads to be hidden inside the stem's front cap. To do that, we need to create what we call counterbore holes. We can change this setting in the Head Type tab and set it to counterbore. We're going to use a bolt with a 13 mm head diameter and an 8 mm thread diameter. So in the head diameter setting, we'll enter a slightly larger value, something like 13.2 mm. For the head height, we'll set it to 8 mm, and for the bottom diameter, we'll also set it to 8 mm. Now we need to manage the hole length. We can't use through all here. It would work for the bottom hole, but not for the top one. What we're going to do instead is increase the value until it just pokes through at the bottom. In this case, 39 mm seems to be a good drilling depth. This value also prevents the top hole from going too deep, which allows us to use the exact same bolts for both the top and the bottom. Since everything looks good now, we can confirm the operation by clicking OK. Next, just to keep up those good habits, we're going to rename the operation to hole front. We've finally reached the stage everyone was wondering if we'd ever get to. I mean, it's been over 40 minutes and we only have half a stem. We're talking about the mirror tool, of course. Here we're going to mirror the entire body, but keep in mind that you can also mirror individual features. To do this, make sure to select the stem body at the very top of the tree view, then click on the mirror tool. What exactly does the mirror tool do? It creates a mirror image of your part. Now take your hands off your keyboard, mouse, or anywhere else I'd rather not know about and lay them flat. Your two hands are symmetrical. In this case, if you apply the operation to your left hand, for example, it would create the right hand. This is incredibly useful for us because it allows us to focus on just one side of the stem and the mirror tool builds the rest for us. By default, FreeCAD creates the mirror across the XY plane, which is completely wrong in our case. We want the mirror to happen along the XZ plane, the same sketch plane we've been using from the start. If you're feeling a bit lost, you can use the gizmo at the bottom. You'll see that the blue Z-axis and the red X-axis form our symmetry plane. Or you can just test all the planes until you get the result you're looking for. So, in the Plane tab, make sure to set it to base XZ plane and click OK to confirm the creation. Next, we're going to work on the rear holes to secure the stem onto the fork's steerer tube. To do that, we'll use the same technique we used a few minutes ago. We're going to create a new sketch and select the XZ plane. Just like with our previous sketches, we're going to enable the section view so we can see through the solid. Then we'll place a point at the rear near the top of the stem. If we want to change the rear length of the stem and have the hole follow that change, we need to reference our point from the edge of the stem. To do this, we're going to use the external projection tool and project the vertical edge on the left. Next, we'll select it and convert it into construction geometry. Just so you know, if you go into the Sketcher preferences, you can check a box that automatically creates external projections as construction lines. It saves you an extra step every time. Next, using the Dimension tool, we're going to set a horizontal distance of 7.5 mm for the point relative to the edge, followed by a vertical value of 7 mm from the red axis. We can now exit the sketch. At the moment, our point is sitting on the middle plane, which means if we run the hole command, it won't pop out on both sides. To fix this, we need to move the sketch. With the sketch selected, go into the Data Properties, then Attachment Offset, then Position, and set the Z value to 16 mm. Now, why are we changing Z and not Y, for example? It's because we're not using the global model coordinates, but the sketch's own coordinate system. Since the sketch is on the XZ plane, the perpendicular axis is Z for the sketch, not Y. It's a bit of mental gymnastics, but remember, the Z axis for a sketch will always be the perpendicular one, no matter which plane it's on. Anyway, we can clearly see in the viewport that the point has moved to the right spot. We're now ready to launch the hole operation. We're going to keep the same settings as before since we want to use the same type of bolts. So we'll set the head type to counterbore, the head diameter to 13.2 mm, the head depth to 8 mm, and the diameter to 8 mm. For the depth, we could just increase the value until it pierces through the entire stem, but the best practice is to go to depth type and set it to through all. Then we can go ahead and accept the creation. On the final part, you can see there are two holes, one on each side, placed at an equal distance from the x-axis. To place the second hole, we're not going to start over by creating a new sketch and a new hole. We're going to do it the smart way, because we're lazy. We'll use a polar array operation. By performing a 180-degree rotation of our existing hole around the x-axis, we'll get the second hole exactly where we want it. To do this, we're going to select the last hole in the tree view and click on the Polar Pattern tool. By selecting the feature beforehand, it allows you to repeat only that specific feature rather than the entire body. By default, FreeCAD suggests repeating along the sketch's vertical axis, which isn't right for us. You need to go to the Axis tab and select the base x-axis. To help you out, you can see the axis as dashed lines, and red corresponds to the x-axis. You'll see the repetition is now in the correct spot. You can then click OK to confirm the creation. Let's not break our good habits. Let's rename that last hole to hole back to keep our file well organized. As it stands, our stem is impossible to mount on the fork because there's no central hole. To fix this, we're going to create a new sketch and select the XY plane to start our drawing. Now, why are we choosing the XY plane instead of the top or bottom face? It's because it's much more stable. By basing our sketch on an origin plane, FreeCAD won't have to recalculate which face the sketch belongs to if the geometry changes. It's a much safer way to model. Back in our sketch, we'll start by using the Section View tool to see through the model. Then, using the Circle tool, we'll draw a circle at the origin and give it a diameter of 28 mm. For our stem to be able to clamp onto the fork, we also need to create a cutout that goes through the entire part. To do this, we need to reference the leftmost edge of the stem. We'll use the External Projection tool to project that edge. If you haven't enabled the option in the Sketcher preferences to get projected lines as constructions lines, you'll need to select this projection and convert it into construction geometry. To create the cutout, we're going to use the Rectangle tool by placing the first point on the projected line and the second point on the circle. It's absolutely vital that this last point is perfectly coincident with the circle. To make sure the rectangle is perfectly centered, we need to apply a symmetry constraint. To do this, select the top point, then the red axis, then the bottom point, and use the Symmetry Constraint tool. Next, using the Dimension tool, we're going to give it a width of 5 mm to ensure there's enough clearance for the clamping. We could exit the sketch now and use the Make Internals option, but we're going to use a different tool to get a single clean profile. If you zoom in, you can see that the rectangle overlaps the circle, so we need to trim these two paths. To do that, we'll grab the Trim tool and click on both lines. Our lines are cleaned up, but that also deleted a constraint, so our sketch is no longer green. By moving the top point, we can see that the circle and the horizontal line are no longer coincident. To fix this, we'll select the point, then the line, and apply a coincident constraint to make the sketch fully constrained again. We can now create our pocket. Just click on the tool. In the task menu, you need to change the mode to symmetric instead of one side, and set the type to Through All. This ensures the pocket cuts perfectly in both directions. Before we move on, let's rename the pocket to Opening Forks. Now, we're going to do a little weight reduction to save some weight inside the stem as shown in the photo. It's going to be very simple. We'll create a new sketch and choose the YZ plane. Next, we'll click on the Section View tool to see through the part. We're going to draw a circle with a diameter of 18 mm right on the origin, and then we'll exit the sketch. Next, we'll start a pocket operation. Make sure to check the reversed box so the cut goes in the right direction. If we choose the Through All option, it will go all the way through, but unfortunately, it will also cut through the two solids at the front, and that's definitely not what we want. Instead, we're going to select Up to Face and try to pick the interior face, but even then it's not working quite right. So we'll select the front face just below it instead, and there we go. You can see the cut stops exactly where we want it. We can now confirm the operation. Next, we'll go into the tree view and use the F2 key to rename the pocket to Opening Inside. Our final material removal will be on the top, again to save a bit more weight. We'll select the top face of the stem and create a new sketch. Then we'll use the Circle tool and draw a 36 mm diameter circle exactly on the origin, and after that we can exit the sketch. We're going to launch a pocket operation, set the depth to 3 mm, and then confirm the operation. And now for the final modeling step that will really polish everything off. We're going to add a 0.5 mm chamfer to the exterior edges. To do this, launch the Chamfer tool and set the size to 0.5 mm. Unlike the Fillet tool, you need to click Select before you start picking your edges. We're going to select the main stem contours, the edges of the two front pieces, and the inner edges at the top and bottom of the fork opening. Once you've made your selection, don't hesitate to rotate your part to make sure you haven't missed an edge somewhere. If everything is selected correctly, you can click OK to confirm the operation. And there we go, we've finished modeling this awesome stem. Congratulations if you've made it this far. You can give yourself a high five because it means you've mastered the basics of FreeCAD now. To keep things even more sparkling, you can rename the last two operations to Opening Top and Chamfer Edges. For those who want to go the extra mile and really put the icing on the cake, we're going to add the 4 bolts and create variables to drive the model. In the industry, you often need to offer your product in different sizes, and that's exactly what we'll do in this final step. But before we do that, let's handle our bolts. We're not going to model them ourselves. We're not cavemen, not anymore. We're civilized people now, even though I'd be pretty happy to see a bunch of cavemen in the comments section. Anyway, for our bolts, we'll need to install a new tool that isn't built directly into FreeCAD. The real cavemen know exactly what I'm talking about. It's the Fasteners workbench. To install it, go to Tools and then Add-on Manager. Next, type Fasteners in the search bar. In my case, I already have it installed, but you should see an Install button, and you'll probably need to restart the software afterward. Then, to access it, go to the Workbench drop-down menu and click on Fasteners. You'll then see a massive library of fasteners appear. There's something for everyone. It's like being in a Haribo candy shop. What's truly exceptional about this workbench is that you just have to select the edges of our stem where we want the bolts and then click on the model we need. In this case, we're looking for the ISO 4762 model. By default, it tries to find the size that fits best, but sometimes it's not perfect, so we have to modify it. In the tree view, we'll select the 6 bolts, and in the data properties, we're going to choose M8 instead of M10. 2 of the bolts are upside down, so we'll select them in the viewport while holding down Control and then check the invert box. That should put them back in the right direction. We also need to adjust their length because the default value isn't right either. Be careful though, as the 4 front bolts are longer than the 2 at the back. We'll select the first 4 bolts and set their length to 30. Then we'll select the 2 rear ones and give them a length of 25. If you have a powerful enough PC, you can generate the threads. To do this, select all the bolts, and in the data properties at the very bottom, you'll see the thread box. You can check it and it will generate the threads directly. Now we're going to move on to the step that will truly take your model from good enough to pro. We're going to create variables to drive our stem. This is often where you find out if you've modeled your part correctly. To do this, we're going to head back to the Part Design workbench from the drop-down menu, and we're going to create a folder named Fasteners to organize our bolts. Next, I'm going to try to clear some space in the tree view by collapsing some features to hide the sketches, and I'll pull down the properties view to make everything look more spacious and airy. To drive our model, we're going to use the Varset tool. This tool allows us to create variables so we can change the dimensions of our model without having to manually modify the sketches or features every single time. To do this, we'll click on the tool that looks like 2 curly brackets. The variable we're going to create will change the length of the stem. On the market, most stems are available in several lengths to suit every rider. In the window that just popped up, we're going to name the variable size, and in the value field, we'll enter 40 mm, since that's the base length we use to create our sketch. In the Varset data properties on the left, we can now see a new table with the label size and the value 40. Here, the size of the stem is determined by the length between the fork axis and the handlebar position. We define this in Sketch 001, which is located inside the pocket handlebar feature. For now, the variable isn't linked to anything, so if we change its value from 40 to 50, for example, nothing is going to happen. We need to go in and link this value to every single distance that can be connected to it. With the variable set to 40, we are going into some sketches to change dimensions. To do that, double-click on the first sketch inside the first feature. The goal here is to link all the horizontal dimensions we created relative to the vertical green axis, which represents the fork axis. We're only going to change the values on the right, since our handlebar is to the right of that axis. I hope you see now why we positioned our rectangle there and referenced all our dimensions from the vertical axis. As you can see, the first value we're going to modify is 66. What we'll do is double-click on it, and then in the window that opens, we'll click on the FX button. This allows us to enter formulas. Since our size variable is set to 40, we need to enter Varset size plus 26 mm to get our base value of 66. What happens then is if we change the size variable to 50, for example, the dimension will automatically jump to 76 without us having to go back into the sketch to change it. Make sure to add mm at the end, otherwise you'll get an error. Also double check that the resulting value is exactly 66 mm. After making this change, you should see the dimension with the label fx next to it, meaning that this value is now driven by a formula. Generally, when you want your file to be driven by variables, you create them at the beginning and build your model around them. However, since this is a tutorial for absolute beginners, I didn't want to overload you right from the start. For this tutorial, using variables is really just a bonus, a pro tip to show you what's possible. For our variable to work, we still need to adjust 3 more sketches. We're going to double-click on Sketch 001 to edit it, then double-click on the 40 mm dimension. In the new window, we'll click on the FX icon and assign it the value Varset size, then confirm and close the sketch. Next, we're going to go into the Pocket Main Shape feature and edit Sketch 002 by double-clicking on it. In this one, we have 2 values to change, 23 and 28, because these are the only ones dimensioned to the right of the green axis. For the top one, our goal is to get 23, so we need to give it a value of Varset size minus 17 mm, which results in exactly 23. For the bottom one, it's the same logic. We'll give it the value of Varset size minus 12 mm, which gives us 28. There's now only one sketch left to modify, and it's the one inside the cutout feature. So let's double click on it. We're looking at the 20 dimension. We're going to give it the value Varset size minus 20 mm, which will result in exactly 20 mm. And now it's the moment of truth. By changing the size value in the Varset, we're going to give FreeCAD quite a workout by asking it to recalculate everything. Depending on how the model was built, reconstruction errors can sometimes pop up. Let's test it with 45 mm. And tada! We are seeing good results. The model is consistently updating without any errors. Let's try a new value, such as 50 mm, to see if there are any further issues, and once again, no errors. Our model appears to be completely stable. However, I recommend you avoid making drastic changes in the values too quickly, such as going from 40 to 80. Instead, try incrementing by 5 mm steps to avoid disrupting FreeCAD significantly. The model has many fillets that could potentially introduce reconstruction errors. In any case, this marks the end of the tutorial. I hope you had a good time and that this will help you on your FreeCAD journey. If you enjoyed it, don't forget to like and comment. I read every single one. And make sure to subscribe. Thanks for watching. We'll see you soon for more projects and tutorials.